Hi, thanks for tuning into this video. This is Brad Munday, one of our data scientists here at Modzy. And today we're going to learn how to package a model using our gRPC and Python container template. Now, before we dive in, it's important to understand model operations, or model ops, and where Modzy fits into this process. So model ops is a superset of machine learning operations, also referred to as ML ops, and refers to the processes involved in operationalizing and managing AI models in production systems. What we're looking at now is just one of many potential reference architectures that organizations might use to form their model ops pipeline, where there is always some data component, there's always a model development and training component, a model deployment component, and then this is really where model ops features differentiate from ML ops. The production inference, monitoring, governance, security, and auditability features that make up model operations tools. This architecture we're looking at now is the one that the Modzy data science team uses, where we might use Python and either TensorFlow or PyTorch to train a model on a few NVIDIA DGX boxes. We'll then use GitHub to version our code and trigger automated container image builds when our model is good to go. We can do this using CircleCI, our preferred continuous integration tool, which then pushes those images we've built into our internal AWS Elastic Container Registry, where we can then access those images to deploy to Modzy. And so when we look at this reference architecture, again, there are many variations of this where you could interchange different tools for the tools that you are using in your own model ops pipeline. And Modzy fits in two key places. The first is during the model packaging and containerization stages, where we can use our Modzy Universal Open Source model container to containerize a model and prepare it for deployment. And the second is where we make it easy and intuitive for all data scientists and developers to deploy models, run inference on those models, and monitor these models in production, including tools for infrastructure management, the ability to measure drift, and even produce explainable model outputs. Now today we're really going to focus on this universal model container and learn how to prepare a model to deploy it to the Modzy platform. Okay, now what do we mean by this universal model container? Well, for starters, we currently provide support for Docker. So you'll need to make sure that you can containerize your model using Docker. And I will say support for all OCI compliant containers is coming soon, but for today, we're going to use Docker. Next, let's talk about the high-level requirements of this container. The first thing that's important is that your model must be fully self-contained, meaning all model weights and dependencies must be included inside your container. And what's great about Modzy is we are completely agnostic of all programming languages, machine learning frameworks, or training tools. So you'll notice in the model code and dependencies box inside this container on this diagram, you see several different programming languages. Again, we leave the development choices completely up to you, so there's a lot of flexibility there, where the only requirement is that your code can be packaged up to meet this specification. And then this container also must have some sort of web server that can respond to calls that will come from our API services. We do support both REST and gRPC protocols, but today we will be using our gRPC template. So in this case, you see 3 remote procedure calls that this container must be able to respond to: the status, run, and shutdown calls that we'll learn about in much more detail later. I will note that our REST template is very similar, with the one difference being instead of these 3 calls being remote procedure calls, they are REST API endpoints. That said, we do really highly recommend using our gRPC template, as we've seen a significant improvement in latency and performance. And this template I keep referring to gives you the option of implementing several features into your model container, but the example we'll walk through today will implement these 4 features on the screen, those being gRPC communication, drift detection, explainability, and custom batch processing. Let's dive in. Okay, here we are on the Modzy GitHub page, github.com/Modzy, where we're going to pull 2 repositories and clone them into our environment to walk through this packaging example. And so if you're following along step by step, you'll need to make sure you have Git installed in your environment. Now, the first repository I want to point your attention to that we'll need to clone into our environment is this basic image classification model. This is a model that we've pulled from the Torch Vision library from PyTorch, just an open source image classification model. It's a ResNet model pre-trained on the ImageNet dataset, and we've configured it into its own repository for example purposes and to play around with. And so you'll notice that we've configured everything into a simple main.py script for ease of implementation and use, and all the usage instructions are included right here. The next repository I want to point your attention to is this gRPC model template. We'll go through this in more depth when we get into the tutorial, but this is the repository I've been alluding to thus far that leverages gRPC protocols and implements the Modzy Open Source container specification. And so the README has a lot of great information that I would encourage you to read in more depth, but you'll notice that there's plenty of usage instructions where we explicitly call out what you need to do to conform your model to this template. We'll have to first move all of our model code into a single model.py script that I'll show you. We then include instructions for model testing and development using Python's PyTest library. And then ultimately, we give you the commands and the instructions for building your container image and testing your newly packaged model to make sure that it runs correctly inside the container. And that's really the main test that we're going to implement today. And then the other thing I'll note here is in this template, we do use Poetry, and the README alludes to it several times. Poetry is a tool for dependency management and packaging in Python. So if you'd like to follow along, there are basic install instructions down at the bottom as well. And if you're interested in learning about the raw specification that we implement in this template, you can go to the documentation page within your Modzy account, where you'll find lots of information, including our API reference documentation, several how-to guides, and pretty much anything you might need to know about using Modzy. But again, if you are interested in reading the raw specification, you can click on this Model Packaging tab and navigate to the Container Specification gRPC page, where we include the raw gRPC specifications implemented in the template that we'll be walking through today. Okay, here I am in my editor. I like to use VS Code, but you can use whatever you prefer. And we'll start by cloning both of these repositories that I just mentioned. So we'll first do the basic image classification model, and next we'll clone the gRPC model template. And once these are both fully cloned, we're going to open up the basic image classification repository. Here we have our basic image classification model, and as a reminder, this is just a open source model we pulled down from the Torch Vision library on PyTorch. And in my environment here, I do have Poetry installed. I'll use that as my Python package manager. You'll need Python version 3.6 or greater. You will need Docker, and that should be all to follow along step by step. Now, let's take a quick look at the contents of this repository. First, we have our data directory with the sample image that we're going to pass through this model to show you what the results should look like, this picture of a dog. We have this download weights Python file that we'll need to download the weights to our repository directly from Torch Vision. So if you're reading along in the README, you'll see that that first step we'll have to do is download the weights. We'll do that in a second. We have our classes file. So this text file contains all of the classes in the ImageNet dataset. And then we have our main.py script. This is the main Python file where we have compiled all of the code, all these snippets you'll find open source on Torch Vision's website for ease of implementation and use. So real quickly, let's go through this. Start by importing the necessary packages we need, including argparse, so we can run this script via the command line. We then define some data directories, namely our data path to point to the dog image, and a weights file path. Once we've defined our data directories, we then define a hardware device. In other words, PyTorch has the syntax where we set it to CUDA if there's a GPU available, and if not, it will be set to CPU. And then in our main method here, we start by loading in the weights file, we define our model architecture as this ResNet 101, and we load this model with our pre-trained weights. We then set our model to the device that we've defined, open up a sample image, open up the labels file, define a data transformation object. In other words, we're preparing our data to get to the correct size and have the correct transformations applied to a format that this architecture expects. We'll then apply that data transformation to the raw image that we read in using the Pillow image processing library. Set our model to eval mode. This is just PyTorch's syntax for setting the model to inference mode instead of training. We'll then pass the process data through to the model, apply a softmax layer, and save out the top 5 classifications of this model, in addition to the softmax probability. The last thing I'll show you real quick is this requirements.txt file with the 3 main Python packages we'll need to run this model. Okay, so with that, let's get started. I do have a package called virtualenv installed in my environment, and so we're going to use that to create a virtual environment to run this in. So we'll start by doing virtualenv, and so we're defining a virtual environment right here. And once this environment is created, we can activate this using this command right here. And so now that we're in our virtual environment, we can install the packages we'll need using pip. Okay, and once these 3 packages are installed, we can clear up our environment a little bit and download the weights file. So per the README, I'm just going to run this download weights Python file. Okay, great. Now that my weights file has successfully downloaded, I should be able to run this main Python file just to see what our model does and what it returns. So again, following the usage instructions in the README, I will run this main.py script, feed it that dog image as input, pass through the ImageNet classes.txt file as our labels, and run this code. And we can see both the results.json file was generated and the results were printed directly to my screen, where I can see that the top prediction was a golden retriever with a 37.735 score, tennis ball, Labrador retriever, soccer ball, etc. And over here on the left, we can see what this results.json file looks like. So this model returns this JSON file with the top 5 predictions and the corresponding confidence score. So now that we know what this model does, let's open up that second repository that we cloned into our environment, the gRPC model template. Okay, let's take a quick look at what's in this repository. First, we have this asset bundle directory. This directory is where we'll define some metadata for each version of the model you decide to package and release. This next directory, gRPC model, is a directory for our gRPC server. And so we have this test directory for you to implement any sort of test that you'd like to build based on your model. And this src directory contains this model server. Now, one of the main benefits of gRPC is that any sort of client application can directly call a method on a gRPC server application on a different machine as if it were a local object. Earlier on, I showed this diagram where I mentioned these 3 remote procedure calls that this gRPC container must respond to. And so as we talk about these methods on a server application, this is exactly what we mean. On the model container side of things, we'll have this gRPC server in addition to a Modzy wrapper around your model code that can respond to these 3 remote procedure calls. And then on the other side of things, we'll have a gRPC client internally within the Modzy platform that will communicate back and forth with your model container. And back to the template, on the server side, we've built that gRPC server for you, so you shouldn't have to touch this Python file at all. I will also note that this model server communicates directly with our model lib directory that I'll talk about in a second. But first, I wanted to show you the model client Python file. Now, as it pertains to this template, this file serves no functionality, but we've included it as a custom gRPC client for you to test the communication between a gRPC server, the one that we've defined, and a client, one that is similar to the gRPC client that exists in the Modzy platform. Again, that will communicate back and forth with your container. We'll get into this a bit later, but what we're going to do ultimately is use this custom client Python file to run some tests. And so we'll want to ultimately pass some data through and run it through this run method defined in this client, where we'll send both a single input and a batch of inputs. More on this later, but this will be very useful for us. Moving down to model lib, this is a library for our machine learning model. We're ultimately going to move a lot of the code from the basic image classification model we showed a little bit ago into this directory, where again we do have a test directory for you to implement any sort of custom testing you'd like, and this src directory, where we're ultimately going to work with this model.py script and paste a lot of our model code in here. More to come on this as well. This protos directory right here contains the protocol buffer used by the gRPC server and client. The scripts directory right here holds a few shell scripts used in various applications throughout the template. This Docker file right here is what we'll use to run and release our model inside a Docker container. So in other words, we'll define a set of commands to set up the environment and then ultimately execute the model server, so that when a gRPC client on the Modzy platform side communicates, it will do so through the commands that we define at the bottom of this Docker file. So we'll come back to this and define this in a little bit as well. And the last couple files I want to show you are the poetry lock, pyproject.toml, and requirements.txt. So this is where you have some flexibility as to how you would like to use this template. As I mentioned earlier, I am going to be using Poetry as my package manager, which means I'm really only going to be working with the poetry.lock file and pyproject.toml, and I'm not going to have to worry about my requirements.txt. Just to show you how you could use either in this scenario, in the Docker file at the end, we'll define some sort of entry point command that will kick off the model server. And if you preferred to use some virtual environment, you could just install the requirements directly using your requirements.txt file using pip, and then just use a Python command to execute the server as a module. Alternatively, we could use Poetry, and that's what we're going to do during development, where we'll need to use the pyproject.toml, the poetry.lock, and then use a Poetry command to kick off the model server. So if you've never used Poetry before, just a quick note here. Poetry is a super useful tool that handles dependency installation as well as the building and packaging of Python packages, where as a user, all you have to do is declare the libraries your project depends on, and Poetry will take all of those libraries and install a version such that there are no conflictions. And all you have to do is construct this pyproject.toml file. Now, this pyproject.toml file will orchestrate my project and all of the dependencies. So in some ways it acts as a requirements.txt file. And so for now, it looks like this. This is the initial version that we include in this template. And so anytime I want to add a dependency that I'll need to run my code, I'll use a poetry add command that I'll show you in a second, and it'll add it to this section right here. And so that's step one. We'll construct this pyproject.toml file. And we won't ever actually have to manually modify this poetry.lock file, but when we're ready to go, we'll use a poetry lock command and then install all of our dependencies in our Poetry virtual environment. Okay, so if you remember, I showed you the requirements.txt file in our non-packaged basic image classification repository that we started off with. And so those three packages were Torch, Torch Vision, and Pillow. Pillow is used for image processing. In this case, I'm going to add both Torch and Torch Vision, but I'm also going to add OpenCV, which is another computer vision image processing library commonly used in Python. And you'll see why in a little bit. It just handles a certain type of data a little bit better than Pillow. So the first thing I'm going to do is modify this Python version. I'm working with version 3.8.7 in my environment, so I'm going to modify that. And then I'm going to add the first dependency, it's Torch. So as you can see here, Torch was added to my dependencies, and it's writing this initial lock file with all my dependencies and their corresponding versions. Next, I'm going to add Torch Vision. And then moving along, as I said, I'm going to add OpenCV as well. And then a couple new packages I will add for some different features that we're going to include in this version. One of them will be Lime Explainability. and then 2 additional packages that we'll actually need for Lime. One's called waitress, and the other is scikit image. Okay, awesome. So now that I've added all my dependencies, I'm going to use this poetry lock command to write our lock file. And then I'm going to install all these dependencies, everything in my lock file, that takes the toml file and defines an exact version, so there are no conflicting dependencies. And I'll install all these dependencies in my virtual environment created by Poetry, just using this poetry install command. And just to make sure that we have successfully installed all of our dependencies and activated a virtual environment, we can just do a quick check here to see which Poetry environments I have access to. And as we can see, this is the virtual environment created when I started adding some dependencies, and we can see that it is activated. So that means that we can access this environment by either directly opening the shell within this environment using a poetry shell command. And as we can see, I could just run normal Python commands in here to kick off that model server. Alternatively, we can kick off whatever command we like with a poetry run, which will then kick off the command we're trying to execute from inside that virtual environment. Okay, so now that my environment is fully set up, it's time to start developing. Alright, now we're going to spend most of the rest of this video working in this model lib directory, specifically in this model.py Python file, where we will move a lot of the model code from our basic image classification repository to this repository. Before we do so, I wanted to take a little bit of a deeper dive into this model server, this gRPC server that we've defined, that again, you won't have to modify at all. So I showed you that diagram of a Modzy compliant container, specifically with this gRPC specification, that communicates back and forth with the Modzy platform and our API services. This server is where we define the 3 remote procedure calls that this container will respond to when the gRPC client on the Modzy side makes calls to this particular container. So I just wanted to show you those real quick. The first call that we define, or method, is this status method, where basically what's going to happen is the platform is going to spin up this model container and make sure that we get a successful response from this status call. And a successful response will include a 200 code, okay, the model will be initialized and spun up, in addition to some other information. Model info, including batch size and other model features, information about the inputs that we'll define a bit later, and outputs and resources. And the second method is this run method. This is where inference will actually happen. So from a user side, they will submit an API call to Modzy to this particular model. They will pass through their own data, and then internally, our gRPC client will take that data and pass it back and forth with the model container and communicate with this gRPC server, all via this run method. And so depending on whether or not the batch processing flag is turned on or off, this method will ultimately submit a call to the handle input batch or handle single input. And so we'll define those in a second in our main model script. And then the third method is this shutdown method, which just shuts down the container. Now, I mentioned this handle single input method and this handle input batch method. These are really important. And this is ultimately the heart of this gRPC template, where we'll put all inference code into one of these 2 methods, or both, depending on how we want to implement batch processing. We notice that this method is coming from this self.model object, which is defined up here in the status route. And so what we're going to do now is do a bit of refactoring and give this a more representative name. So I'm doing this a bit backwards, but we'll see that up top we import our model base class from this model.py Python file. So now that we've made this refactor, and I'll make the change again in model.py, we won't have to touch this model server. As a reminder, we've written this in a way that it's compliant with the gRPC remote procedure calls that our platform expects to a point where you don't have to do any other additional work here. So let's exit out of this model server Python file and get into the bulk of where we're going to be working, and that's in model.py. Before we forget, let's make sure that refactoring carries over to this. So now our base class is called gRPC Basic Image Classification. Again, a bit more representative of the model that we're packaging up. Okay, so in this class, we first have our Init Constructor. So this method will execute anytime that our gRPC Basic Image Classification model is called, which, if you remember, happens in that status remote procedure call in the model server. So since this corresponds to that status call, we are going to want to put all model initialization tasks and all tasks that we only need to execute once for inference, so that when a user wants to submit an inference call to this model, the status remote procedure call will be executed once, and the model will be good to go for as long as the container is spinning, and that run call can be hit as many times as needed to submit inference. So we will fill this in a second. And then the next two methods we have here are this handle single input and handle input batch. And if you remember, one of these methods will always execute in that run remote procedure call. And so if you wanted to only implement a single input for every inference, you'd only want to fill in this handle single input method and raise a not implemented error in this batch method. Alternatively, if you wanted your model to support batching, which is something we are going to implement in this case, we will want to fill in this handle input batch method. Now let's talk about the parameters for each of these methods. First, we will get some model input, and we can expect that input to come in the form of binary contents, or bytes, for each of the input files that we define in our YAML file. We'll do that in a minute as well. And then we're going to want this method to return a dictionary, where the key of that dictionary is a string that corresponds to the output file name that we also will define in our YAML file. And the value of this dictionary will be the predictions of this model, again in binary form. The other two parameters to this method are this detect drift and explain Boolean variables, where if set to true, we will be expected to return either a drift or explainable output as a part of our model output. And so in the template form, you'll notice some example code for a simple greeting message given any sort of text that you input. And then again, in this handle input batch method, closely follows the structure of the single input method. However, in this case, if we did want to implement this, we would expect a list of different inputs, or a batch of inputs, coming in the same format. So we can expect a list of binary input data, and in exchange we will want to output a list of string to binary output matching as well in a dictionary to represent the predictions for each input in the batch that this method receives. Okay, so let's start transferring the code from our main.py Python file and start filling in this model.py script. We'll start by copying over the packages we need to import for our model code to run. And so a lot of this is the same as in that main.py script, with a few exceptions and additions, OpenCV being one of them, and then Lime and scikit image being two others. We're then going to want to define some data directories. So again, we'll need our labels file and then our weights as well. So what we can actually do is copy both of those things over to our src directory right here. Alright, we can delete this helpers function, as this is just there for the example code. We can get rid of this import statement as well. Alright, so now we have our weights in here and our labels file for the ImageNet dataset. Moving down, we will skip and come back to these for now. But let's fill in our initialization constructor. So if you remember, we will define our device based on the hardware that we have available. This is PyTorch's way of letting the code know whether or not we have access to a GPU or CPU. And so we'll define our device and set it as an instance variable called self.device right here. We're then going to load our model in. Again, loading that ResNet 101 architecture and loading the pre-trained weights that we've saved in our weights directory into that model. And then we will set our model to the device that we've defined. So again, this is a PyTorch specific syntax, but basically once we've defined our device, we'll have to set the architecture and any data that we're processing to that device to make sure that everything is processed on the correct infrastructure. Once we've done that, we can set our model to eval mode. So this is PyTorch syntax for saying we are going to be running inference, freeze the weights, and we're not going to be doing any training. And then we can open our labels file. So remember, everything that we're including in this init constructor, we only want to execute once. These are one-time tasks that can be loaded and initialized one time and be good to go for inference several subsequent times thereafter. So we'll load in our labels file based on the labels directory we defined up here. And then the last thing that we'll want to include here is our data transformation object. So as a reminder from our basic image classification repository, this data transformation object will take our data and transform it to the correct format expected by this architecture. Okay, so I think our init function in our constructor is good to go. Let's now start assembling our handle single input and handle input batch methods. So as a reminder, we are going to implement batch processing should the user want to submit a batch of inputs to this particular model. We are going to get rid of everything we see here. That's for example purposes. And because we're going to implement batch processing, we are just going to force the batch method, making our lives a little bit easier. So we really only have to implement one of these methods. By passing the input to this method, again, this is just a single input, passing it through to this batch method as a list, which is the same input format this batch method expects, and only take the first output every time there's just a single input. And so we'll just return this result in the single input case, and then draw our attention to this batch case. So to start off, we will delete the existing template code there, just an example. And it is important to note here that because we are processing a batch of inputs in this method, we will need to handle any error catching on an individual input by input basis. As noted here in this commented out section, if we do not handle errors on an individual input basis, then any error that occurs in the batch of, let's just say, for example, 8 inputs, it will throw a fatal error and result in the entire batch failing. So in the example I mentioned, if this method's receiving a batch of 8 inputs and one of them happens to be bad that throws an error, if we don't handle the error catching on an individual basis, then the entire batch will fail. So we'll need to account for that. And so let's start there. Since we're dealing with images here, we're going to essentially loop through each input in this batch. So as a reminder, the input to this method is a list of inputs, where each input is a dictionary, where the string is the input file name that we will define in the model YAML file, and the value is just the binary bytes of that input. So let's loop through this list of inputs. And what we'll first do is extract the actual bytes from the dictionary in each individual input. So we're saying that for a model input in a given batch of inputs, we're going to extract the bytes from this dictionary here. And in this case, we're indicating that the key of this dictionary should be image. We'll define that in our model.yaml file and make sure they're consistent. Next, we're going to process this image. And so here you see that I've defined this self.preprocess image in bytes format method. Let's go define that. Where for this method, we'll define a single parameter as input. Again, we're expecting the data to come through as raw bytes format. we will just add some commentary into this method to define the arguments, inputs and outputs, and what we expect it to return. So the input will just be the image in bytes form, and it will return a NumPy array of the preprocessed image in addition to the original shape of the input image. We'll need that shape when we implement explainability in a little bit. So using OpenCV's imdecode method, again, this works well with data that comes in bytes format. We will pass through our raw bytes, and we'll use this NumPy from buffer method to extract our data. And at this point, we should be able to work with this data, reshape it, do any resizing, and be able to pass it through ultimately to our architecture. Again, we are going to store this original shape when we implement explainability a little bit later. And we'll wrap this in a try except statement to return a meaningful message if there's anything wrong with this error. The last thing we'll need to do is resize this image as a preprocessing step to the shape that this architecture, the ResNet 101 that we're working with from PyTorch, expects to receive. And so then this method will return both the data and the original shape. All right, great. So now that we've defined our preprocessing method, we can move on in filling in our input batch method below. So whether or not this data is valid, we will pass through the raw image, the raw bytes, to this preprocessing method and get the actual data and the data's original shape, the image's original shape back. And then we're going to check if this data is either a NumPy array or a dictionary. If it's a NumPy array, we're assuming that it's a valid image. And if it's a dictionary, we're assuming that there's some error. And so what we'll do then is add that particular error message in dictionary form to our indexed errors. Otherwise, we'll append it to our images and keep track of that original shape. This ensures that we are successfully handling any errors that may occur in a batch on an individual input by input basis and only pass the network legitimate input files or images. All right, so now, if there are any valid images in our batch, in other words, if we have successfully appended some NumPy arrays to this image list right here, we're going to concatenate them all into a single NumPy array that we can then pass through our architecture for inference. It's important to note here that in order to be able to pass a batch through, or in this case, a multi-dimensional NumPy array that represents several inputs or a batch of inputs, you need to make sure that your model code can handle batches or can run inference on batches. Most common machine learning frameworks, PyTorch, TensorFlow, Keras, scikit-learn, they all support this, so it shouldn't be an issue if you're using any of these, but it is something that you do need to account for. So once we have concatenated our batch of legitimate images into a single NumPy array, we're going to pass it through this batch predict function. So we need to define another new function where we make sure that our architecture receives this batch of input in the correct format. So under my preprocess image bytes, I'm going to define a batch predict method that just takes some images in as input. In this case, we're expecting images to be either a 3-dimensional NumPy array for the single input case, or a 4-dimensional array, n number of legitimate images in our batch. And we're doing it this way because we're only implementing that batch method, but in order to support the single input case, we need this to work for that as well. So the first thing we'll do in our batch predict method is check if the shape of the image's input is indeed 3, or indicative of a single input. And if that's the case, we will just add a dimension to make it consistent with the multi-images case. In other words, we're going to make a 3-dimension NumPy array to 4 dimensions. And here's where some of the code from our original main.py script, way back in our basic image classification repository, will come into play. Specifically, we're going to take our images NumPy array and transform each image in there with the transformation which we defined in our contract method. And then ultimately set the entire input to the device that we're working with. So in this case, we are working with GPUs, and this will be set to a Torch tensor to prepare it to be sent through the model. And once we've successfully prepared our inputs, we can then pass it through our model for inference. So this line right here looks exactly like it did in our original repository. And then to keep things consistent, create an output that's intuitive for users to understand, we're going to apply a softmax layer so that the output for each class is a probability score. And lastly, in this batch predict method, we're going to convert our tensor output probability object to a NumPy array so we can return something that's easy to manipulate in post-process to save out and return to the user. Okay, awesome. So we've now defined our batch predict method. And so at this point, we can expect this preds object to be a NumPy array of shape n by c, where n is the number of inputs in a batch, and c is the number of classes in an ImageNet dataset. So now it's time to do some post-processing on these inputs. Just like before, in the original repository, we're going to return the top 5 predictions. So let's now define a post-processing method where we will take our top 5 softmax probabilities and match them with their corresponding labels. So at this point, it's important to remember that this softmax preds input is an m by c NumPy array. That means that we're going to have to map back the top 5 predictions for n number of inputs in a batch and keep that all organized and return it in a clear, intuitive way. And to do so, we're going to loop through this softmax predictions NumPy array, storing the top 5 labels and top 5 probabilities for each set of softmax probabilities. So what we'll start to do is sort the predictions for a given input in decreasing order. We'll then take that index and assemble the labels from our labels file for each of those indices, and do the same for the probabilities, and append both the labels and probabilities to this list. And once we've done that for each set of predictions in our softmax preds NumPy array, we will return both the top 5 probabilities and the top 5 labels. Alright, so now we've gotten to a point where we've concatenated our batch of inputs, we've sent that through our batch predict method, and taken the NumPy array that holds the predictions for each input and pass that through our post-processing method, which leaves us with 2 lists, the top 5 probabilities for each input in the batch and their corresponding labels. And given these 2 lists, we can pass them through a formatting method that will basically just match probability to corresponding label for each input in a batch and format it in the correct way to meet our 2.0 specification. And what our platform will do with that 2.0 specification, if it is a classification model, is measure output drift over time as users submit more inferences to this model. So let's define this format results method. So we'll go under our post-processing method here, and define this format results method that will take 2 lists as input. 1, all of the prediction probabilities, and 2, their corresponding class labels, and basically stick them into a dictionary where we'll segment out the class and the prediction with their own keys, class and score right here, and stick all that into a larger dictionary where the key is just this class prediction string right here. Now at this point we have successfully formatted our inference results. Given there is a possibility to implement input drift and explainability, we'll use this last chunk of code to combine all of our components for the output together, where one component is the inference results, another is an explainability object, and a third is a drift object. In this example, we're not going to implement any input drift object. We will do explainability in a second, but for now we'll leave that be, and assume that the explain flag is turned off, so that for now this will just be none. And then we'll pass through our inference results coming from this format results iterator that we just built, our explanation result, which for now is none, and our drift result, which also for now is none, into this get success JSON structure method. This is included in our template that I skipped over earlier. that will basically just throw those three components of our output into a larger dictionary denoted with this data key. It's also important to note that we've included this method returning a JSON file with the key results.json. So we'll define this as our output file name in our YAML file. However, if you're working with a different type of data or you want to name your output differently, you would want to switch this right here as long as you are consistent with how you define it in the YAML file. You'll see that in a second. But if you are returning a JSON structure as your output, feel free to leverage this method that we've included in our template. Okay, now we're ready to test out this model code that we've conformed to this template. But before we do so, we have to fill out some metadata about this model, some information that our platform will use when users are submitting inference and submitting their own data to this model container. So in our asset bundle directory up here, included in the template, we have this directory with the version name of our model. You'll want to make sure that you name this consistent with how you version your model. So for now, we'll keep it as 0.1.0. And in this directory, there are a few different subdirectories and YAML files, all of which are explained in the README in more depth. But for now, we're just going to edit this YAML file. Here's where you have the opportunity to document everything about your model. What's the version of this model, or name of the model, and who built it? What's a short description of what this model does? You can include technical details, including an overview of how the model was built, any underlying architectures used, training data used, and training processes implemented, any validation information, in addition to some input and output details. Now, all of this information is optional to fill out, but it will save you some time when deploying your model, because all this information will auto-populate your model details page. Moving down to the portion of this YAML file that you do have to fill in, we'll start with our inputs. This is where we'll define our inputs file name. We do this because in the scenario that there are multiple inputs to this model, our platform needs a way to map the user-specified input data to the correct input. So if you recall, in our handle batch method, we took the model input from the list and the dictionary and extracted the bytes from the key named image. So we'll call our input image. And then under accepted media types, this is where you have to include the MIME type of this particular input. And so to view all the MIME types for different data types, you can view this website right here. But our platform will use this as a validation check so that if a user tries to submit a video or a text to a model that only accepts JPEG or PNG encoded images, our platform would throw an error exception. So in this case, we are going to include both the JPEG and PNG MIME types. We can then give this particular input a maximum size, so we'll say 5 megabytes, and a description of what this input should be. So we'll just say a JPEG or PNG encoded RGB image. And we'll then need to do the same for our outputs. In this case, there's a single input image and a single output results.json file. And so we'll keep this as results.json, as that's what we have specified in this output object, right here, results.json. So we have to make sure that this matches what we define in our YAML file. So we're good to go here. Make this a JSON file, the 1 megabyte maximum size, and the description of this output will be top 5 predictions and corresponding confidence score. Moving down to the last mandatory portion of this file, we can fill in some information about resources that this Docker container will need to run most optimally. Starting with memory. So this weights file is a decent size, so we'll allocate 4 gigabytes of RAM here and indicate that we want this to run on 1 CPU and 1 GPU. Moving down a little bit further, we have to fill in these timeout values for both status and run. So remember, this container will respond to 3 remote procedure calls: status, run, and shutdown. What we're saying here is we're giving our platform a timeout threshold to kill any processes if these procedure calls take longer than the time that we allocate. So in this case, this model usually loads pretty quickly, but we'll allocate a 60-second status threshold and also a 60-second run threshold. And then we do need to fill in some flags In this case, we'll say that the maximum batch size for this model is 8. So no matter how many inputs a user may submit for batch processing, our platform will make sure that this model receives no more than 8 inputs in a single batch at a given time. All right, now that we've defined some metadata in this YAML file, we can exit out of this. And the last thing we'll need to configure before submitting a test to this code that we've now written is this model client Python file that I mentioned earlier. So as a reminder, when this container spins up and runs, the server will have to be executed automatically. What happens on the Modzy side is there's a gRPC client that communicates back and forth with the gRPC server. So for the purposes of testing in this template, this model client really serves no functionality other than the fact that it gives us a custom script to test our client-server interaction with. So we've built this run method that creates an input based on the tests we would like to submit, and then ultimately sends either a single input or a batch of input, or both. And so we see here we had this single input and a batch of input. For now, I'm going to include this explain equals false flag. We'll change that to true when we implement explainability in a few minutes for both a single input and batch of inputs. And below, where we'll actually execute this run method, we need to modify the inputs we're going to be working with. So if you remember when I showed you what this model does in the non-package repository we started with, we were working with this image of a dog. So I'm going to start by copying this dog in here. And I'll move this to the parent directory. And then we're going to define a data path to pass this dog through our newly configured code. All right, and down below for our test inputs, we are going to change this dictionary a little bit. So the key will be the input file name that we just defined in our YAML file, so image. And instead of this string of text, we will open the image path of this dog image, read it as bytes, and be able to pass it directly through our run method right here. All right, and now that we've configured this client, we should be good to go in testing our model. And to do so, let's open a terminal. If you followed along in the README, you'll see that we have to actually have 2 terminals open. One to kick off the server, and one to kick off the client. And in this scenario, the client will make remote procedure calls to the server, which will then read directly from our model.py script. Okay, so in my first terminal, I'm going to kick off the server. So if you remember, we created a virtual environment using Poetry, and to run a command in that virtual environment, we will use this Poetry run, and then we're going to run our server as a Python module. And in doing so, we see the logger print out to the screen that the server is running on port 45,000. Now, in a new terminal, we're going to also use this Poetry run command. But this time, we're going to kick off the model client, again, as a Python module. And we should see some things printed out to our screen as these 2 tests that I showed you are executing, both a single input and a batch. As we can see, we get this JSON file out right here with our class predictions, Labrador Retriever, Golden Retriever, and none for both explanation and drift. You'll notice that we can segment this out by the example where we pass through a single input, where we receive a single output, and a batch of input, where we're submitting the same image 8 times in a batch, and we get an individual output for each input that we submit. So this is exactly what we were hoping would happen. And we know that our inference results portion of our code does indeed work. Okay, now the last thing we're going to implement today is explainability. So in our handle input batch method, we have this explain parameter, where if set to true, we want to return some explanation for our predictions. This is where there's flexibility. If you have your own proprietary explainability solution, you're welcome to include it here. We're about to implement Lime, which is an open source solution for image classification and text classification. But again, this is up to you as the model developer. So down below, under our conditional statement, where if we're dealing with some valid images and we've run inference already, we're going to paste in this segment of code where if the explain flag is true, we'd like to compute explainability for each input in this batch. And the way we're going to do so, as I said, is through Lime, where we will produce an RLE mask, which is a very common mask when we're talking about explainability for image classification and segmentation. So what we're going to do is for each image in the batch of images we're working with and its corresponding original shape, we're going to pass it through this getExplainability method. So let's define that now. Below our formatting results, we will define this getExplainability function, where this function will take the image that we'd like to run explainability on, some prediction function. This is a requirement when you're using Lime, where the input of this prediction function is a NumPy array of your inputs, and it outputs a NumPy array of size images to number of classes with prediction probabilities. And then this method is going to return an RLE mask, as I mentioned. So we've imported Lime up at the top of our Python file and included this explain instance, where we're including our raw image, the prediction function, which in this case is that batch predict method, top labels we'd like to get an explanation on, and a few other pieces of information. To learn more about what's going on here in Lime in general, I'd encourage you to follow this link you'll be able to find in this repository that is public on our GitHub page as well. And then once we run the explainability experiment, we will do some post-processing on the mask and return it in RLE form. So you notice part of that is this RLE encode mask function that we've also included in the script above. All right, so now that we know what this function does at a high level, this should make a little bit more sense now. Again, we'll call this explainability method for each input in our batch, using the batch predict method as the prediction function required by Lime with the original shape. And then we'll take the RLE mask returned by this method and format it in a way that will work well with the Modzy interface when you're working with a model that produces explanations with its predictions. Okay, now it's time to test out our explainability component to the output that we've just created. So if the explain flag is turned to true, we will add the explanation result to our final output. And to do so, it's pretty simple. All we're going to do is open up this client again. And if you remember, earlier I turned this explain flag off. So we'll turn these both to true and run the same test we did earlier. And again, once I've opened my terminal, I'm going to run the server in one terminal and run the client in another. So we can use the same command we just used a little bit ago to kick off the server. And once we see that the server is indeed running, we can open up our second terminal and run the client. In this case, we do see it's connected, and this will take a little bit longer since we're going to produce an explainability object for each output. So we're sending a single input we can see right here, and this time we get the output printed to our screen, where in addition to the class predictions, it also includes an RLE mask. And RLE stands for run length encoding, which is a simple method for storing binary masks. So instead of outputting an entire image of this mask with each of the RGB values for every pixel, RLE format provides a list of start pixels, starting from the top left of the image, working down, followed by the number of pixels included in the mask. And so if we look at the mask RLE list within this output object, that first value, 357005, is our first start pixel. And then the following value, 12, is the number of pixels after that start location included in the mask. And then the 638 number that follows is the next start location, followed by the number of pixels included in the mask, or 12 again, so on and so forth, throughout the rest of this list, which ultimately is a much more efficient way of defining binary masks. And we can then see that the entire batch of 8 inputs also completed, where we receive the same output object for each input in the batch. So this means that we've successfully implemented an explainability solution. In other words, we've taken our plain vanilla image classification model, conformed it to this template, which now supports batch processing in batches of maximum size 8, and explainability, all using our gRPC communication. And there's one last step we have to go through, and that is to construct our model container to ensure that we can replicate everything that we've just tested right here inside the container. Okay, so we'll start by opening up our Docker file, where we will construct our container, or in other words, we'll set up an environment inside the container, similar to the environment that we were just running where it successfully passed those tests, to run and release this model inside a container. So the first line of our Docker file is the base image we're going to start from. And in the template, we provide this Python 3 base Docker image. For the purpose of this model, we are going to change that slightly and use this NVIDIA base image that has a version of CUDA we'll want to use since our model can run on GPU. We're next going to add a series of commands that will need to use some of the packages we'd like to use in this Linux environment. Next, we are going to install the same version of Python that we were just using in my local terminal, which is 3.8.7. And then we'll modify this section slightly, where we'll want to make sure that we have everything we need inside the container for the model to run. So we'll make sure that we're in the correct directory. We'll keep the gRPC model directory. We'll copy over our entire model lib directory in our asset bundle. And then we're also going to copy over this dog image so we can run this client test inside the container. We can keep some of this unchanged, but then at the bottom, where in the template we give you a couple options. If you are using pip in a different sort of virtual environment to directly install your dependencies inside the container, you could use this. However, to replicate the test I just ran, we're going to use poetry again. So we'll delete this section and comment out this section. We're going to add our pyproject.toml file and our lock file. We're going to install poetry, and then using poetry, we'll install all the packages, in turn creating a poetry virtual environment inside our container. And then we'll close out our Docker file with an entry point so that when we run this container after the image is built, this command will execute, which should look familiar since this is the same command I was using earlier to kick off our server. So what this means is once we've tested this image and it works, we've pushed this image into the Modzy registry, anytime a user goes to submit an inference job to this model will spin up and the gRPC server will automatically kick off. Meaning, when the gRPC client on the Modzy side decides to communicate with this container, it will do so directly with this model server through those 3 remote procedure calls. Alright, now that our Docker file is finished, let's build the image, spin up the container, and run that same client test inside the container to make sure that our container works. So we'll start by using a docker build command, where we'll include this t parameter to indicate what we're going to call this image or tag it as. And so we will call this gRPC image classification. And the last argument to this command points to the Docker file that we'll build this container image from. And so since we're in the same directory, we can point to that with a period, and we will build this image. Okay, so the image has successfully built. It's called gRPC image classification. So now it's time to run this container. So again, we're going to do this in 2 separate terminals, simulating how the Modzy platform will communicate with this Docker container. So the first thing we'll do is just spin up the container using a docker run command. We'll include this runtime equal NVIDIA argument because this container can run on GPU. And then we'll also include this interactive argument so that when we run the container, we will see exactly what's going on inside. And then we will add this p parameter, which will forward the port that the server is running on inside the container to a port locally in our environment right here. And so by default, we've set the PSC model port environment variable within the server to be 45,000. And we will forward that port to port 45,000 on our local machine as well. This will allow us to test the containerized server from a local Python client that will emulate what happens when the Modzy platform communicates with this model container. And lastly, we'll point to the container image that we want to run, which is just a gRPC image classification. And in doing so, we will see that the gRPC server is running on port 45,000, just like before, which is great. So in a separate terminal, we can see which containers we have running in our environment. And we'll notice that our container that we just spun up is indeed running. We can go back and forth between the 2 terminals and see that it is still running. So that's great. And what we can also see is that we've forwarded the port to our local port 45,000. This means that we can run the custom gRPC Python client on our end that we've already been using, because that client will try and connect to the server on the local port 45,000 as well. So let's use the same command we did earlier to test out our containerized server. And what this is doing is exactly simulating how the gRPC client on the Modzy platform side will communicate directly with the gRPC server inside this containerized model. So again, we're just running this gRPC client as a Python module. And in doing so, what we'll notice is that we connected to the server on 45,000. We'll start by sending a single input, just as we did before. And what will happen is we should get the output printed to our screen right here. We'll then follow it by sending a batch of input to this running container. And what we'll notice is the output printed to our screen for each of the inputs in the batch of 8 that was sent in this test. And again, these outputs look exactly as they did before. This should be familiar, which is great. That means that our containerized server does successfully communicate with a gRPC client outside of this container, which is exactly what we need to happen, as the Modzy platform will communicate with our container in a very similar way. And in switching back to our other terminal, we can see all the information that the server side printed out via the loggers included in the server to our screen. That being the progress bars for the explainability on both the single input and the batch of input, and that the server successfully processed each item in the batch of size 8. So we've now walked through the entire process of taking a vanilla basic image classification model, one that we took directly from PyTorch, and conformed it to this 2.0 specification, implemented by this gRPC template we provided, where this model is now fully containerized, leverages gRPC communication, can support batch processing on GPUs, and returns explainable outputs, which is a pretty powerful combination of features to deploy into production with Modzy. If you'd like to take a deeper look into the example we just walked through and play around directly with the model we just built, you can visit our GitHub page, and everything that we just went through is in this new repository called gRPC Packaged Basic Image Classification, where you can go walk through all the code yourself, and there's some usage instructions here for building the image and running some tests. So feel free to do so. Thanks so much for tuning in today. Now that you've learned how to use this gRPC template and package your own model, it's time for you to now start deploying these models to the Modzy platform and running inference on them in production.